see a simple DC circuit. This is a battery of voltage V. This is a resistor of resistance R. These are the conducting wires. A and B are the 2 points on the conducting wire. So if someone asks, is there any potential difference between A and B? And if it is, what is the potential difference between the point A and B? We know that is conventional current or positive currents. It flows from the positive terminal to the negative terminal outside the battery. So going by this logic, potential of A should be greater than B. That is potential, because the positive current is going from A to B, and we know that is positive charges, positive current flows from a higher electric potential to lower electric potential. So if the current is flowing in this direction, so it means the potential of A should be greater than potential of B. But that is not the case. Reason being, the resistance of this conducting wire is 0. If you remember a case what we did in Newton's laws of motion, we said that is the tension in an ideal string that is equal to 0. And if you remember, that is how we drew the force diagram. Over here, if suppose there is a mass of 5 kg and over here there is a mass of 10 kg, and suppose we have applied a force, let's say 30 Newton, and to prove that is the tension is same throughout this ideal string which doesn't have a mass, which is inextensible, what we did, we had drawn this diagram. So we had drawn the force diagram of this string, and over here we assume, let's say the tension is T dash, and this way the tension is T. Because it is going this way, so we said that is T dash minus T, that is net force. We had been using that is net force is equal to mass into acceleration. So net force is T dash minus T. Mass of this, because this ideal string, it is 0 into A, so that's why T dash is equal to T. Obviously, if the mass of any object is equal to 0, then the force which is required to move it, to accelerate it, that is equal to 0. It is a similar kind of a logic over here. When the resistance is equal to 0 of these conducting wires, though that is once again we are talking about perfection. This is assumption only, that is these are perfect conductors. There is no perfect conductor. To simplify the things, we consider the resistance of these conducting wires is equal to 0. So once we have considered that is resistance is equal to 0, then to push the charges, that is to push the conventional current into this direction, we do not need any potential difference. Or even if we apply that is VAB, if we wish to apply V is equal to IR, VAB, that is we say, suppose we say VA is greater than VB. So VA minus VB is the potential difference. When we say V is equal to IR, V is the electric potential difference between the 2 points which are connected by a resistance R, and I shall be the current which shall be flowing through it. So VA minus VB is the potential difference is equal to I is I. What is the resistance of this? Resistance of this is equal to 0. So this comes out to be 0. So that's why VA is equal to VB. So we can very safely we can say that is, if the wires, they are conducting wires, all the points on these conducting wires, they are at the same potential. Going by this logic, let's try to find out what is the equivalent resistance between A and B. We have just found that is the equivalent resistance between these 2 points A and B. It comes out to be R by 3, where R is the resistance of one single resistor. So here we see, if we call this point a junction as X, we call this as Y, and we call this as Z. So here we see that is A and X, they are on the conducting wire. Resistance is over here only, right? This is resistance, this is a resistance, this is resistance, rest all they are the conducting wires. So over here we see that is whether we talk about the A or we talk about the X, this all the points, they are on the same potential to this. We cannot jump a circuit element, that is any resistance, etc. But all the points now A, X and Y, they are at the same potential. So what we do is, we say we combine over here A, X and Y, they are at the same potential. Similarly, we see that is B and Z, they are the same potential because this is conducting wire only, and on the conducting wire all the points they are the same potential. Similarly, this is also a conducting point, and we call this as, let's call this point as L. So B, Z and L, they are at the same electric potential because this is conducting wire only. So B, Z and L, they are the same potential. So B, Z and L, they are the same potential. We can combine it as one. Now let's see what are the resistance like. One resistance is between X and L. Where is X? X is in this, L is over here. So we connect it by one resistance. Obviously, we have joined between X and L, we have joined one resistance, so its work is done. We also see that there is a resistance between L and Y also. There is one resistance we see between these two junctions. L and Y. So Y is here, L is here. So this is the second R. Its work is also done, job is also done. And we also see that there is one more resistor between Y and Z. Where is Y? Y junction lies in this, and Z junction is over here. So between Y and Z, its work is also done. So this is R. So this is over here, that is A is here, B is here. So the equivalent resistance between A and B, if you have to find out, so 1 by R equivalent is equal to all these resistors, they are in parallel, 1 by R plus 1 by R plus 1 by R. So this is 3 by R. So R equivalent is equal to R by 3. And this is the same result which we had got earlier.